Let me start this session with some simple questions. Efforts to resolve the black hole information paradox has led to different perspectives on the internal structure of black holes. What is your understanding of the internal structure of black holes?
So let me first say that classically there's no problem and there's no ambiguity. Everybody agrees the internal behind the horizon is described by Einstein's general theory of relativity. It gave us this nice clear picture of what a black hole is. But recently it's been shown that there are problems with this when you include quantum mechanics. So first, if you treat the matter quantum mechanically, but keep the black hole space-time described classically according to general relativity, what one finds is that there is a very large volume inside a black hole. The singularity in a black hole is not at a point in space, but it's actually in your future. And if you enter the black hole, you discover there are very large regions of space. And if you just count the degrees of freedom of a quantum field, you quickly find that you have more states than there should be, more states than expected from the black hole entropy. So people have recently proposed ways of dealing with this. Sometimes people say that there's some extra gauge symmetry in these theories. These states are not all different. Sometimes people say that the inner product has to be modified so that these states which look orthogonal are not really orthogonal. So that's one problem that people are dealing with. Another one is more radical. When you include more quantum effects in the gravity side, you come up with an idea of a firewall, which means that black holes, when they evaporate and they've reduced to maybe half their original size, suddenly the singularity lies on the horizon and you can't enter it all. You asked what my view of the interior is, and I have to say, I don't know. I mean, I'm following these recent developments. I find it a very interesting question, but I've not yet come to a conclusion about which is correct or what the actual state is of an old black hole. I find the firewall hard to accept, but the arguments are pretty convincing. So I think we'll have to wait and see what happens.
My next question is on wormholes and would be very interesting to many of the science enthusiasts. So your recent work has focused on creating wormholes. Could you please explain the key aspects of this non-perturbative creation process and comment on if wormholes can ever be made in reality?
So it's been known for a long time that you can pair create electron-positron pairs in a very strong electric field. This is a quantum mechanical process, which was worked out by Schwinger originally. But since matter and energy are the same thing, E equals mc squared and all that, this is a process which has been known to happen quantum mechanically. So what's been shown more recently is that you can also pair create oppositely charged black holes. So a black hole with a positive and negative charge can be quantum mechanically created in a strong electric field. And this is described by a Euclidean solution of Einstein's theory called an instanton. And when you look at that solution, what you discover is that the black holes, when they're created, have their horizons identified. So that changes the topology of space and indeed produces a wormhole. So I would say that yes, this is an allowed process. It's something which in principle could happen in our universe. The rate would be extremely low for any sort of macroscopic or big size black hole because it's exponentially suppressed, and the probability with ordinary electric fields of producing observable black holes is probably much, much longer than the age of the universe. So it's something that explains why we haven't seen them. Now, there is something else. I mean, you can ask about whether the wormhole is traversable. And most wormholes that you produce this way are not traversable. They will actually pinch off and form a singularity before you can actually go through them. In fact, before anything can go through them, even light doesn't have a chance to make it through before the wormhole pinches off. So you can change the topology of space, but you can't actually go through it as an ordinary wormhole. However, very recently, it's been shown that you can make traversable wormholes using quantum matter. The key is that you need negative local energy density. And most ordinary matter classically has positive energy density, but quantum mechanically, matter can have negative, at least regions of negative energy density. And so it was shown that you could take a wormhole, which has already existed, and put a quantum state of the matter in such a way that you can actually go through from through the wormhole before it collapses. So what we did was to combine the idea of a pair creating a wormhole from nothing, with this recent idea of making it traversable. And we found conditions under which that's possible. So you could create a traversable wormhole. Unfortunately, the conditions we had to assume were a little bit unphysical. We had to change the boundary conditions of space so that they are something called asymptotically anti-de Sitter, that space asymptotically approaches negative constant curvature, and that actually produces an extra attractive force to keep the mouths of the wormhole from accelerating apart. Normally, you have oppositely charged particles in an electric field, they'll accelerate apart, and when the wormhole gets very long, the quantum negative energy gets very small, and it can't stop it from collapsing. But we found a way to create the wormhole and not have it accelerate apart, and that way we could keep the wormhole traversable. That, I think, is, well, I don't see how to do that in the real world, unfortunately.
And lastly, before diving into the in-depth questions about your work, I would like to ask another question. What is this concept of holography in physics, and how can it be understood in relation to everyday experiences in science?
So the idea of holography started with the discovery of Bekenstein and Hawking in the early 70s, that black holes have an entropy which is just proportional to their area, to the area of the surface of the black hole. This was surprising because most systems, like a gas in a box, has an entropy which is proportional to their volume. And since the entropy is related to the number of degrees of freedom or the number of states of the black hole, it suggests that you can describe the state of the black hole just by looking at this two-dimensional surface surrounding it, and not by looking at anything inside. Well, this was extended in the 1990s by to Hooft and Susskind to suggest that maybe holography is not just a property of black holes, but a general property of quantum gravity. And it was all made much more precise with Juan Maldaceni's discovery of gauge gravity duality, which is this remarkable statement that a complete quantum theory of gravity with certain boundary conditions, in fact, these asymptotically anti-de Sitter boundary conditions I mentioned earlier, is completely described by a non-gravitational gauge theory living in a lower dimensional space, essentially living on the boundary of space at infinity. And so this is called holography because it's very much like an ordinary hologram, where you have a two-dimensional object which is able to reproduce a full three-dimensional image. And so it's, well, when it was first proposed, it seemed quite ridiculous, and it was thought that we could disprove it very quickly. But after 25 years now, it's withstood many tests. It seems to genuinely be true, and it's quite a remarkable statement that quantum gravity really is holographic and can be described by this lower dimensional, in fact, non-gravitational theory.
All right. So apart from black holes, your work has also focused on different gravitational objects like black strings, Kaluza-Klein bubbles, and p-branes. Could you please explain these concepts and how they influence our understanding of higher dimension space-time?
So first of all, there's several motivations for considering higher dimensional spacetimes. String theory predicts that space has more than 3 dimensions, and it's been known since the 1920s in the work of Kaluza and Klein that you can unify the known forces, in particular the electromagnetic and the gravitational force, by assuming space is, say, 4-dimensional and not 3-dimensional, and just thinking about a theory of gravity in this one higher dimensional space. So that led us to think about black holes in higher dimensions. And we discovered that they have a lot of Well, they're in some sense less constrained than black holes in the ordinary 3 dimensions, and there's lots more objects one can consider. So first of all, if we just go up 1 dimension, there's something called the black string, which can be thought of as just an ordinary black hole in 3-dimensional space, and you take its product with a line. Or if the extra dimension is compact, you can think about taking its product with a circle. So that gives you a 1-dimensional extended object, which is surrounded by an event horizon. So that's something we call a black string. Now, if you have more than 4 spatial dimensions, if you add more than 1 extra dimension, you can have extended black holes which are extended in more than 1 dimension. So these give you black branes. There's a generalization of a black membrane. So in, say, 5 spatial dimensions, you can have a black hole cross R2, and in higher dimensions, you can take, just take the product with extra spatial dimensions. So these are black branes. The interesting thing about these black branes is that they can carry a new kind of charge. There is the analog or a generalization of a Maxwell electromagnetic charge, which is carried by these higher dimensional extended objects. And you can write down solutions of general relativity and higher dimensions with these analogs of Maxwell fields and find solutions of these black branes with charge. And you discover that they have an extremal limit. In other words, there is a maximum charge that a black brane of a given mass or a given energy density can carry. And those extremal black branes turn out to be exactly the sort of gravitating description of something which had been discovered in string theory, which are known as or not black. In string theory, they were known as just d-branes. It was discovered by Joe Polchinski in the 1990s that string theory is not just a theory of strings, but there are these non-perturbative objects, which are extended higher dimensional objects, which are like these branes. And what we found was the sort of gravitational description of them when you put a lot of them together and you build up the gravitational field. Now, you also mentioned Kaluza-Klein bubbles, and these are a very different sort of object. If we take the simplest Kaluza-Klein theory, so this is just adding 1 extra dimension of space, which you assume is a circle. So the sort of vacuum would be ordinary 3-dimensional Euclidean space across a circle. And now there is another solution, which is called the bubble of nothing. And what that looks like is you take your 3-dimensional space and cut out a ball. You just cut out a solid ball at some radius, and that would normally produce an inner boundary to your space. But because you have an extra circle over every point, you can imagine that that circle shrinks as you come in from infinity and smoothly caps off on the sphere, which is the boundary of your bubble. So if you fix an angle and just look at the sort of circle direction and the radial direction, you get something which looks like a cigar, a long cylinder which is capped off. And so now you have a space which has no inner boundary. There's a minimal 2-sphere. And so these are called bubbles of nothing. And there are lots of solutions like this in this higher dimensional general relativity. They were in fact discovered by Edward Witten when he found that the Kaluza-Klein vacuum, Euclidean space across a circle, is non-perturbatively unstable to actually nucleating one of these bubbles of nothing, which then expands out and actually ends up taking over all of space. So we've studied them in various ways, and we've discovered there are lots of different kinds of bubbles. There are small bubbles, which actually collapse to form black holes. Bigger bubbles expand. You can put fluxes on these bubbles and stabilize them, and they have various applications or things in 5-dimensional general relativity.
Thank you. And so going on next, defining energy in gravitational theories is a tough task, but your work with Stephen Hawking led to a better understanding of the gravitational Hamiltonian. Could you please elaborate on how this definition of total energy affects our understanding of energy in space-time, and what are its implications?
There's no local energy density in gravity. But people have define total energy in certain special cases. Asymptotically flat spacetimes, there's a notion of total energy, and asymptotically anti-de Sitter, they found another notion. So what Stephen Hawking and I did was to give a general framework for defining energy in any spacetime which asymptotically approaches a static solution of the field equation. We did that by starting with the action, and it's just being careful about including all the surface terms and doing a Hamiltonian reduction. And we found a formula which is applicable now to, so it's sort of one framework for which we can discuss all of these different cases. It reproduces the known total energy in the cases where it had been worked out before for asymptotically flat and ADS, but it's also applicable to some more exotic situations. For example, if you have a cosmic string, which is a one-dimensional extended object with some energy density, general relativity says that at large distance, space looks like a cone. You have some deficit angle. And our formalism can be applied to that case and give you a total energy or total energy per unit length for cosmic strings this way.
So moving on, in your paper on bulk reconstruction, you propose a novel approach to reconstructing the metric of holographic spacetime. Could you please elaborate on the practical applications of this reconstruction method in addressing the long-standing issues like resolving singularities, understanding the behavior of spacetime in extreme conditions, or even shedding light on quantum gravity?
One of the main problems with holography, I mean, we have this general idea, but in practice, it was not clear how to reconstruct the space-time metric from this dual non-gravitational theory. People had worked hard to see how you get fields. If you start with so basically the ground state or the vacuum, which is just this anti-de Sitter space, and you put fields, test fields on it, people had shown how to describe those in terms of boundary operators or boundary states. But it involved using the field equations in the bulk and extrapolating to the boundary in various ways. So we wanted a way to reconstruct the metric itself, not just perturbations on the metric. And we found that you can do it using something called light cone cuts. So these are basically, if you take any point in the bulk, look at the boundary of the light cone and how it intersects the surface at infinity, you get a series of these cuts. And we showed that if you knew the cuts, you could get the metric everywhere, metric in the bulk up to an overall conformal rescaling. So we actually reconstruct the conformal metric from these light cone cuts. But the more interesting thing is that we were able to show how to determine these cuts just from the boundary theory. So we have a way of getting the metric in the space-time up to this overall rescaling just from the dual theory. Now, we did this in a limit where the metric is really classical. This is the so-called large N limit in the gauge theory, talking about like an SUN gauge theory as a dual theory. So that construction by itself doesn't directly tell us about quantum space-time. But I'm thinking at the moment about ways to generalize it, to apply it to situations where we could, maybe see aspects of the quantum nature of space-time. That's still, work in progress.
Thank you very much. So since the publication of vacuum configurations for superstrings in 1985, the field of string theory has seen significant developments. Could you discuss how these findings and concepts from this paper have influenced our subsequent research in string theory and its evolving landscape?
Yeah, so that paper introduced a new way of treating the extra dimensions of space. String theory predicted that space had 9 dimensions, space-time was 10-dimensional, so we had 6 extra dimensions of space, and we show that if you take a 6-dimensional compact manifold with certain properties and look at the effective theory you get in our usual 3+1 space-time, you got a theory which was very similar to the standard model of particle physics, the actual world that we see. So we called these special six-dimensional spaces, which did this, a Calabi-Yau space for various reasons. And well, that paper has been enormously influential. I think it now has over 3,000 citations, by far my most highly cited paper. Of course, it was written with Edward Witten, Andy Strominger, and Philip Candelas. But it sort of opened up a new way of thinking about string phenomenology, about relating string theory to the real world. This is actually an area that I haven't pursued much in my subsequent career, but many people have. And initially, we thought that the conditions we were imposing on these spaces were so restrictive that there would only be a few solutions. There would only be a few Calabi-Yau spaces. And so we would have, an easy way of predicting the low energy properties of our three spatial plus time world. But over time, people have found more and more ways of constructing these six-dimensional spaces and getting our interesting features in our world. So that's produced this huge landscape now of string vacua. So the early ideas now seem very naive, that there would only be a few solutions, and this has now been a whole industry of studying these Calabi-Yau compactifications. People have generalized our work in many ways by adding fluxes associated with some of these, analogs of Maxwell fields. They've wrapped branes around certain cycles in these six-dimensional spaces, studied singularities in these six-dimensional spaces, and all of this leads to interesting physics in the lower dimensional sort of remaining three plus one dimensions. So it's been a big industry. There are now many solutions. It's made the problem of finding a string phenomenology that actually describes our world much harder.
So another interesting direction of your work explores the holographic description of superconductors. Could you elaborate on the holographic principles in understanding this seemingly different field of superconductivity?
Holography relates a theory of gravity to a non-gravitational theory. It seemed natural to ask if we could find gravitational analogs of other non-gravitational phenomena, such as superconductivity. In an ordinary superconductor, there's a critical temperature, and below that, pairs of electrons with opposite spin bind together to form something called a Cooper pair, which has spin 0 and non-zero charge. And these bosons can condense, and you get some charge condensate, which is responsible for the superconductivity. So to find a gravitational dual, what we did was we first said, okay, we need a gravitational analog of the temperature of the superconductor, but that's described by a black hole, where the Hawking temperature of the black hole is the temperature of the dual theory. Then we needed to describe many particles, sort of a particle density, and that turns out to be related to a charge on the black hole, if you look at the holographic dictionary. And finally, we needed an analog of this condensate, this charge condensate, and we modeled that with the charge scalar field. And so what we asked ourselves is there a way in this gravitational theory of gravity plus a Maxwell field plus a charge scalar to find a black hole which was stable without a scalar field at high temperature, but became unstable to forming a scalar field at low temperature? And this was not something I had seen before, and black holes normally are just simply stable, and they don't want to turn on scalar fields outside the horizon. This was part of a no-hair theorem, that there should not be matter just sitting outside the horizon. But it turns out that with the boundary conditions you need for holography, this asymptotically ADS boundary conditions, this is exactly what happens. That black holes at very low temperature do become unstable to turning on the scalar field, and this is the gravitational dual of the superconductor. We then computed things like the conductivity and found that the DC conductivity was infinite, just as a superconductor. And we were able to even do things like construct a Josephson junction, which is two superconductors separated by a narrow gap. And when they have different phases of this charged condensate, a current will flow even without any applied voltage. And we found a gravitational solution which did all of that and reproduced the expected behavior of a Josephson junction. So initially, when we discovered this, we were hoping this would have some impact on understanding the high temperature superconductors, because the standard theory of superconductivity is a weakly coupled theory, the BCS theory, and the high temperature superconductors discovered in the 80s were believed not to be weakly coupled. It turns out in holography, we can't describe detailed properties of the high temperature superconductors. We can only describe these general properties. And it is true that holography relates a gravity theory to a strongly coupled gauge theory. So the main lesson was that, if you believe in holography, this gravitational instability was a new mechanism for a new kind of instability of the dual theory, because you could see it clearly in the gravitational side, and it must be indicating some sort of instability of the strongly coupled theory to producing this charge condensate, which is what you need for the superconductor.
So what is the future direction of your work, and what are some questions that you would like to tackle in the next 5 years?
In the back of my mind, I mean, there's always these big questions, which I'd like to say something about. I don't know if I'll succeed in the next 5 years, but I would like to know, for example, what a quantum black hole is. I mean, we always define a black hole in terms of the classical geometry. You need a well-defined causal structure in order to say what points can causally communicate with infinity. But quantum black holes shouldn't have a definite causal structure. The light cones should fluctuate. And what do we even mean by a quantum black hole in full quantum gravity, not a semi-classical approximation? What do we mean by quantum space-time? And what happens near singularities like the Big Bang and the singularities inside black holes? So these are big questions which are always in the back of my mind. I've tried approaching them in various ways throughout my career, and I'll keep trying to find models or ways of hopefully saying something about it in the future. But maybe more near term, I've been working very recently on a new kind of singularity. We believe general relativity gets modified in the sense that sort of new high energy degrees of freedom or even quantum effects can produce corrections to general relativity involving higher curvature terms, terms like, the Riemann tensor cubed and things like that. And normally those higher curvature terms come with very small coefficients, and we expect them to be totally negligible when dealing with sort of large macroscopic objects and away from regions of large curvature. But what we've discovered very recently is that extreme Kerr black holes, maximally rotating black holes, are very sensitive to this type of correction to general relativity. And any non-zero correction will make the horizon singular. So these rapidly, maximally rotating black holes actually get a singular horizon. So that example is not something we can hope to observe or have any astrophysical consequences, because we don't believe astrophysical black holes are exactly extremal. But this mechanism, we're now thinking about other ways in which these small higher derivative corrections might have a big effect, and looking for other examples of things like that, which I'll probably keep working on for a while.
Thank you for this amazing session. And lastly, what piece of advice would you like to give to our young audience?
Okay, well, one comment is often students, they're given a problem. I mean, our work is very theoretical, and they get involved in these sort of abstract ideas, and maybe lose sight a little bit of the real world. And so I'd like to remind students that I think it's a very good idea to have, in mind, let's say just order of magnitude estimates for basic quantities like, the mass of the proton, mass of the electron, basic properties of the world, and to know something about real black holes. What kind of real black holes have we actually seen? To know about the supermassive black holes and the gravitational waves, which have been discovered recently. I mean, these are amazing aspects of our field and of the general field of gravitational physics. And even though, my students don't work on that, we're working on the more abstract quantum gravity questions. I think students should, at least keep aware of all of these discoveries in astrophysics related to our field. And even theoretically, I mean, students work on a problem and get, very involved in the technical details. But I think it's always important to keep the big picture in mind. What are the big questions that this is ultimately hoping to answer, and to make steps toward, to just keep that in mind as well.